Well, good afternoon, good morning, good evening, whatever the case may be. Welcome to this study guide for the AZ-700 certification exam prep. In this video, my goal is to give you a high-level introduction to the AZ-700 certification exam. My name is David Branscombe, and I'm a security architect at Microsoft. Now, this particular session is going to be relatively short, so you can listen to it while you're eating lunch. Maybe you're on the treadmill, or you could just be spending the last 30 minutes of your workday doing some self-improvement. Focus of these study sessions all link back to the stated objectives for the AZ-700 exam. The title of that exam is Designing and Implementing Microsoft Azure Networking Solutions. So specifically, what I'm going to be dealing with in this session is the third set of exam objectives, and that is focused on the designing and implementing of routing in your Azure network. So let's hop right into it, shall we? All right, section 3, design and implement routing. So to help understand virtual network routing, let's take a look at the diagram here on the slide. So this is an example where you have a virtual network that includes 3 separate subnets. So the subnets are private on the right, you've got DMZ in the middle, and you've got public on the left. So in the DMZ subnet, there's a network virtual appliance, which we just talked about in the previous section. And you want to ensure that all traffic from the public subnet goes through the NVA to the private subnet. So what you want to do here is create a route table. So you click through the wizard to create the route table, and the new route that you want to add to the route table is named toPrivateSubnet. So we add this route to the route table. And we see that the private subnet is 10.0.1/24. And the route that we're configuring here, as you see from the drop-down menu, uses the virtual appliance. Notice that there are other choices for the next hop type. So we can choose virtual network gateway, we can choose virtual network, internet, and we can choose none. So now the virtual appliance is located at 10.0.2.4, so you can add that subnet to the route table. Now what we have here is a path from the public subnet through the DMZ to the private subnet that goes through the virtual appliance. So at a very high level, that's how virtual network routing is essentially configured. Now, force tunneling is another interesting topic. So with force tunneling, what you're doing is redirecting or forcing any traffic that is bound for the internet back through your on-premise location using a site-to-site VPN tunnel in order to do inspection on that traffic or perhaps doing auditing on that traffic. So this is a pretty critical security requirement for many enterprise IT policies. If you don't configure force tunneling in those environments, any traffic that is bound to the internet from your VMs that are hosted in Azure is always going to go straight from the Azure network infrastructure out to the internet. So it doesn't give you the option to inspect or audit the traffic using the infrastructure that you have on premises. That type of unrestricted internet access can potentially lead to information disclosure or other types of security breaches. Now, the box down here in the lower left corner makes the point that force tunneling cannot be enabled after the firewall is created, and the subnet that the force tunneling uses is going to have the default name Azure Firewall Management Subnet. So you may want to keep that in mind when you are planning out your infrastructure. Let's switch gears just a bit and talk about load balancing. Now, I know I'm beginning to sound a little bit like a broken record, but you're going to need to know the different SKUs of load balancer. So there is a basic SKU, a standard SKU, and a gateway SKU. We're only going to talk about the first two in this in this discussion. Each SKU, of course, is catered toward a different scenario, and it's going to have differences in terms of scale, the features that are available to it, as well as pricing. So Microsoft recommends using the standard load balancer. So standard load balancers are what you would use for load balancing network layer traffic when you have high performance requirements, when you want to achieve ultra low latency. The standard load balancer can route traffic within and across regions, and it can use availability zones to achieve high resiliency. Basic load balancers, on the other hand, are more limited, and they're better suited for things like small scale applications that don't need high availability. They don't necessarily need redundancy, and they don't need to take advantage of things like availability zones. Now, there are two flavors of load balancer as well in terms of where they sit in the architecture. So there's public and internal, as you see highlighted here in the diagram. So your public load balancer is what's going to provide external connectivity for your virtual machines inside your virtual network. So the load balancer is going to translate private IP addresses on your VMs to a public IP address on the load balancer. So public load balancers are used to load balance internet traffic destined to your VMs. An internal or private load balancer, which we see on the bottom of the diagram, is used when you only need to connect to private IP addresses at the front end. So internal load balancers are used to load balance traffic inside a virtual network. A load balancer front end can even be accessed from an on-premises network in a hybrid scenario. So this will even work, you'll even be able to access it from an on-premise network if it's configured correctly. So you just want to make sure that you're configuring it in the proper scenario here, depending on the security needs and so on. The last bullet point on the slide mentions cross-region load balancers. So a cross-region load balancer helps you to ensure that your service is available globally. It can span multiple Azure regions. So if an entire region fails, the traffic is routed to the next closest healthy regional load balancer. So as with all the other discussion points that we've gone through so far, make sure you know the SKU differences, when to use standard, when to use basic, what the capabilities of each of those are. The SKUs play very heavily in the exam, so making sure that you understand what capabilities exist is going to help you pass. Continuing on the topic of load balancers, a load balancer rule is used to define how incoming traffic is distributed to all the instances within the backend pool. So a load balancing rule maps a given front-end IP configuration and port to multiple backend IP addresses and ports. So an example would be a rule that you create on port 80 or port 443 to load balance web traffic to a dozen backend web servers, right? Each of those web servers has their own IP address, but you're using the load balancer IP, the public IP on that load balancer to distribute the traffic to those web server instances. An inbound NAT rule. What an inbound NAT rule does is forward incoming traffic that is being sent to a front-end IP address port combination. The traffic is sent to a specific virtual machine or instance in the backend pool. So the port forwarding that's required here is done by using the same distribution logic that the load balancer itself uses. An outbound rule, which we see in the diagram, we've got outbound rule 1 and outbound rule 2. This configures your outbound NAT for all virtual machines or instances identified by the backend pool. So this rule is going to enable instances that are sitting in the pool in the backend to communicate outbound to the internet or to other endpoints. So why would you use an outbound rule? So an outbound rule is going to allow you to explicitly define SNAT for a public standard load balancer. And so this configuration allows you to use the public IP addresses of your load balancer to provide outbound internet connectivity for your backend instances. What this allows you to do is perform things like IP masquerading. It allows you to simplify allow lists, and it reduces the number of public IP resources that are required for your deployments. So the outbound NAT is a pretty useful concept. All right, moving on to the Azure Application Gateway. So the Azure Application Gateway is a web traffic load balancer that lets you manage traffic that is inbound to your web applications. So traditionally, your load balancers operate at the transport layer, and they route traffic based on source IP and port to a destination IP and port. Application Gateway has a little bit more logic to it. It has a set of components that combine to route requests to a pool of web servers and to check the health of these web servers, including, as you can see in the diagram, it's going to have a front-end IP, which is the diamond, the green diamond on the left. It's going to have listeners, the first rectangle, the blue rectangle in the middle. And then it's going to have rules, which is the second blue rectangle on the right. Now, it is really, really important that you understand how these listeners and rules play into the operation of an application load balancer. So please, please, please make sure that you read the article that I referenced there very, very carefully so that you understand what each of these features is doing. And on one of the upcoming slides, I think it might be the next one, there's some links to specific configurations that you're going to need to know when you take the exam. So there is also a requirement when you set this up that you have to choose between either manual mode or auto scaling mode. If you have auto scaling enabled, the application gateway and web application firewall are going to scale up and down based on application traffic requirements. When you use auto scaling, it gives you better elasticity for your application and eliminates the need to guess at what size you have to provision your application gateway at, and even how many instances of the application gateway you have to provision. So it also gives you the option of saving money by not requiring the gateway to run at a peak provision capacity for any unanticipated maximum traffic load. So if you don't use auto scaling, you have to provision for kind of a worst case scenario. But auto scaling allows you to provision as the need arises. So manual is the opposite of that. So with manual, you can choose, how many instances of application gateway or WAF you're going to provision, and the problem is if there's more traffic than the application gateway or WAF can handle, you could end up with traffic loss. So you have to specify the instance count when you deploy it in manual mode. And so for that reason, it's generally preferred to use auto scaling if you're not sure of maybe burst types of traffic or heavy usage time periods during the week or month or things like that. The third set of bullet points down talks about creating a backend pool. So a backend pool is something you use to route requests to the backend servers that are then going to serve that request. So if you look at the the diagram in the picture here, the backend pool can be comprised of virtual machines, virtual machine scale sets. It can be a set of public IP addresses. It can be internal IP addresses, FQDNs, multi-tenant backends like Azure App Services. You can even create an empty backend pool with your application gateway, and then after the fact, add backend targets to the backend pool. The last bullet point talks about health probes. So Azure Application Gateway, by default, monitors the health of all the resources in the backend pool and automatically removes any resource that's considered unhealthy from use by the pool. It also automatically configures a default health probe when you don't set up any custom probe configuration. So the monitoring behavior works by getting an by making an HTTP GET request to the IP address or the FQDN that's configured in the backend pool. And if you're using the default probes, if the backend HTTP settings are configured for HTTPS, the probe uses HTTPS to test the health of the backend servers. All right, so I mentioned that you need to know listeners, routing rules, HTTP settings, and then down at the bottom here, rewrite and redirection. This is probably one of the most important slides in this entire deck, not just in this section, but in the entire deck. So spend some time understanding the concepts on this slide. So at a very high level, a listener is an entity, a logical entity that checks for incoming connection requests by looking at the port, the protocol, the host, and the IP address. When you create an application gateway by using the Azure portal, you also create a default listener by choosing the protocol and port that will be used for that listener. There are two types of routing, as we see in the diagram on the right-hand side. There is path-based routing and multiple site routing. These are really, really important concepts to understand for the exam. So if we look at path-based routing sends requests that have different URL paths to different pools of backend servers. So for the top one, we see that the request is going to contoso.com/images/wildcard. And on the bottom, it's going to contoso.com/video/wildcard. So based on the URL, the web application firewall is going to, or the application gateway rather, is going to route the traffic to a different set of resources. In the bottom image, we've got multiple site routing. And so what this is doing is configuring more than one web application on the same application gateway instance. So with multi-site configuration, you register multiple DNS names, there's C names, for the IP address of the application gateway, and you specify the name of each site. The application gateway uses separate listeners to wait for the requests that are destined for each site. Each listener is going to pass the request to a different rule, which can route the request to servers in a different backend pool. So what we've got in the diagram here at the bottom is a rule on the web on the application gateway that says if a request comes in for contoso.com, send that request to the Contoso pool of VMs. If a request comes in for fabricam.com, a rule kicks in that sends a request to the Fabricam pool. So again, you're really, really going to need to know how this multiple site routing works. Think about like scenarios where they give you a full path, a full URL, and ask you, how will this be routed, or which servers will this be routed to? Redirection and rewrite rules are also really, really important, understanding how those work. So make sure that you take a look at the link there for troubleshooting session affinity issues on Azure Application Gateway, so you understand how to troubleshoot redirection. So again, take some time, study this slide in depth. This is going to be worth several questions on your exam, so it's worth the effort to spend some time on it. Azure Front Door. So Azure Front Door is a global scalable entry point that leverages the Microsoft Global Edge network to make it possible to scale your web applications globally. Now, while both front door and the application gateway that we just talked about are operating at layer 7 of the OSI model, so they're using HTTP or HTTPS, the primary difference between these two is that front door is a global service, whereas application gateway is a regional service. So front door can load balance across regions. Application gateway allows you to load balance between your VM containers that exist within a scale unit within a region. To determine the health and proximity of each backend for a given front door environment, each front door environment periodically is going to send a synthetic HTTP or HTTPS request to each of the configured backend resources. The front door is then going to use the responses that it gets from those transactions to determine the best backend resource to route your client request to. So essentially, it's just checking to see which resources have the highest availability, lowest latency, those sort of things. Azure Front Door does support end-to-end TLS encryption. Front Door TLS or SSL offload will terminate the TLS connection, decrypt the traffic at the Azure Front Door, and then re-encrypt the traffic before forwarding it on to the backend resources. So since connections to the backend happen over the public IP address, it is strongly recommended that you configure HTTPS as the forwarding protocol on your Azure Front Door to make sure that you're enforcing end-to-end TLS encryption from your client machines all the way through to the backend. You might expect, the way that front door behaves is in part determined by what else? SKUs. So the SKUs that are being used make a difference. In the documentation for Azure Front Door, you'll see that there are multi-site and basic listeners. So the question is, how are those requests handled? So there is a version 1 SKU and a version 2 SKU, and that has less to do with kind of the similarity between like basic and standard, and it's more a versioning difference. So for the version 1 SKU, requests from a client are matched according to the order of the rules and the type of listener. Okay, so if a rule with a basic listener comes first in the order, that rule will be processed first, and it will accept any request for that port and IP combination. If that isn't your preferred behavior, however, you can configure the rules with multi-site listeners first, and then push the rule with the basic listener to a lower position in the list. For the version 2 SKU, multi-site listeners are processed before your basic listeners by default. Okay, so for version 1, the basic listeners come first in the order. For version 2, the multi-site listeners are processed first. I've used the term backend several times in this discussion. So a backend refers to a web application deployment within a region. So Front Door supports both Azure and non-Azure resources in a backend pool. So the application could potentially be in your on-premises data center. It could be located in another cloud provider like AWS. Either one of those types of scenarios is supported. Front Door backend or backends refer to either the host name or the public IP address of your application that serves those client requests. You should not confuse a backend in this scenario with a database tier or a storage tier. That's not what we're talking about. Backends should be viewed as the public endpoint for your application. Make sure that you understand how to set up a custom domain in front door for a URL, how you would configure HTTPS on a custom domain. And there's a good link there that can help you to understand that. And then again, talking about redirects and rewrites, understand how those are used, and make sure that you understand WAF logs, and make sure you're comfortable reading the JSON for WAF logs. So this box may be on the wrong slide, but nonetheless, make sure that you do research that information. So the link at the bottom of that, the larger box about understanding WAF logs, there are some examples of the JSON in the WAF logs. Read those over. Make sure you understand where you could configure things to make something work if there was a failure, or how you could reconstruct that JSON so that failures are eliminated. Azure Traffic Manager. So Azure Traffic Manager is a DNS-based traffic load balancer. It allows you to distribute traffic to your public-facing applications across global Azure regions. It also provides your public endpoints with high availability and quick responsiveness. So Traffic Manager uses DNS to direct client requests to the appropriate service endpoint based on a chosen traffic routing method. And there are 6 traffic routing methods that are used to route your network traffic to service endpoints. So when you're setting up your Traffic Manager profile, as you can see from the drop-down, you have 6 different options for how you would route the traffic. It can be based on performance. You can weight your traffic to certain regions, maybe that have more resources in that region. You can rate it by priority, by geographic location. There can be multi-values that you use, or it can be based on subnet. Traffic Manager also supports 3 different types of endpoints. So you can support Azure endpoints. So in that case, you'd be load balancing traffic to, for example, a cloud service, a web app, a public IP address in the same subscription within Azure. You could also use an external endpoint. So you'd use this type of endpoint to load balance traffic for your IP addresses, your FQDNs, or for services that are hosted outside of Azure. So just like we were talking about on the previous slide, this can be either on premises or with a different hosting provider. Then there's the concept of nested endpoints. And this may come up on the exam as well. So you might want to do a little bit of research into nested endpoints. So you'd use a nested endpoint to combine Traffic Manager profiles to create perhaps more flexible traffic routing schemes to support the needs for larger, more complex deployments. So with nested endpoints, you would have a child profile added as an endpoint to a parent profile. So both the child and the parent profiles can contain endpoints of any type, including other nested profiles. So make sure that you understand that concept. The top red box gives a good scenario that you might want to kind of be familiar with. So if you have multiple Traffic Manager routing methods configured and one endpoint, for example, you've got a web app that's an endpoint. If that fails or it's degraded, how will the traffic be routed? So you might be given a scenario where you have multiple traffic routing methods, and the preferred one is no longer going to work. maybe it's based on performance and the endpoint is no longer performant. How will that traffic be routed? So make sure that you understand how that works. The last slide for this section, virtual NAT. So we've really already talked about NAT to a certain extent in some previous slides. But network address translation, which is what we refer to as NAT, simplifies your outbound only internet connectivity for virtual networks. NAT is fully managed. It is highly resilient in Azure, and you can support dynamic workloads by simply scaling NAT. When it's configured on a subnet, all the outbound connectivity uses the static public NAT IP address. Now, the diagram that's kind of hidden behind the wizard that you see here, it shows different variations of inbound and outbound traffic and how it would be NATed. NAT and the compatible standard SKU features are aware of the direction that the flow was started, whether it's inbound or it's initiated from outbound. So inbound and outbound scenarios can coexist together. Those types of scenarios will receive the correct network address translation because the features are aware of the flow direction. So make sure you know some of the limitations of NAT, such as the fact that it is not supported with IPv6 right now. Another thing that you'll need to understand is the last bullet point on the slide here, troubleshooting NAT connectivity, and what happens when you have SNAT exhaustion. So how is that addressed, or how would you fix that type of problem in your environment? So that brings us to the end of this section. The next section will deal with how to secure and monitor networks. And that brings us to the end of this section. I hope it was beneficial for you. Please be sure to check out the study guides from Thomas Maurer and Charbel Nemnom as well. And you have the links to the study guide, the deck. So be sure to check out the other videos in this series. And I hope you do well on the exam.